Hello, I'm Tom Overbye. I'm a professor in electrical and computer engineering at University of Illinois, specializing in power systems. And in this slide set, I'm going to provide some introductory coverage to power system blackouts. Okay, as we all know, our modern society is more and more dependent on a reliable electric power grid. So when the lights go out, life pretty much grinds to a halt for most of us. Blackouts can be quite costly, with some estimates saying that the cost just in the U.S. alone will be over $100 billion per year. However, the impact of individual blackouts can differ substantially. They range from very large events that can affect millions to very localized events that affect just a few customers. On this slide, I've got a picture here on the top that shows the damage that was caused to the transmission grid in Quebec due to an ice storm they had, I think, back in 1989. And here, obviously, they've got some pretty substantial damage to their towers. The picture on the bottom here shows a more localized blackout that was caused by, of all things, a trampoline here blowing from a nearby home into their 115 kV transmission substation, causing a short, localized outage. And while it only affected a small number of customers, it was certainly quite costly to remove that trampoline. Okay, most blackouts are caused by problems in the distribution system, that is the lower voltage lines. And this picture here of a family of squirrels indicates that small animals such as squirrels are actually a cause of a large number of blackouts. As an example, I just recently had the power go out at my house. The utility came out, and sure enough, they found that there were two squirrels that were jumping around on some of the local distribution lines. Squirrels got nice long bushy tails, and if they just happen to jump between the phases, they cause a short circuit. And it's bad news for the squirrel. It's bad news for the customers. The two dead squirrels got carted away by the utility, and for us, power was rapidly restored with not too much inconvenience. Okay, in discussing blackouts, it's useful to apply statistics to get a feel for the impact they have. But in doing so, I'm certainly reminded of the quote by Mark Twain here about lies, damn lies, and statistics. Applying statistics to blackouts is fraught with peril because their effects can vary so substantially. You might have a short outage that affects a few customers that might last seconds or minutes versus a widespread outage that affects millions of customers that can last days or perhaps even weeks. So it's hard to just use statistics to get a full feel for this, but certainly they can be useful, and they are used quite a bit. Okay, IEEE actually has a standard. It's 1366 from the year 2000 that defines some of the standard indices that are used when we're talking about blackouts. One of these is the System Average Interruption Duration Index, SAIDI there. That represents the average amount of time the supply to a customer is interrupted per year, expressed in minutes per year, and then per customer. So to calculate this value, what the utility does is they take the total minutes that people were outaged, they divide by the total number of customers they have, and that gives them this value expressed in average amount of time per customer. Related to this is the System Average Interruption Frequency Index, which represents the average number of times per year the supply to a customer is interrupted. Okay, and that's expressed in terms of interruptions per year. Now the S in both of these indicates that these indices apply to the entire system, and certainly some people are going to have higher values and some people are going to have lower values. Where I live is actually at the end of a distribution feeder that goes through a whole bunch of trees. It's an area that has a lot of squirrels in it, a lot of trees, so I actually tend to lose power, I think, much more often than some other customers. One of my colleagues who lives in town says that his power seldom goes out, where I'll have a number of outages each year. Okay, so these are system averages. Two other statistics are what are called the Customer Average Interruption Duration Index, CAIDI. That tells the average time to restore service by just averaging over the customers that were outaged. So in the previous indice, we took the total minutes out divided by total customers. This takes the total minutes out but divides it just by the customers that were actually outaged that year. The second customer index is the Customer Average Interruption Frequency Index. That takes the total number of interruptions averaged, again, over only the customers that actually had interruptions. So the utility figures out the number of customers who had interruptions during the year and uses that in the denominator. There are several other indices as well. For example, in all these indices, they make a differentiation between a momentary outage, which for most utilities is one that lasts less than 5 minutes, versus a more sustained outage. Okay, however, in calculating these indices, the IEEE standard defines something called a major event day, MED. The major event day is a day in which this SAIDI index exceeds a threshold, and then all the indices are calculated with the major event days removed. So this might correspond to something such as a large ice storm, or perhaps you've got a hurricane, or you've got a tornado that is causing a large number of customers to be outaged. The idea is a major event day is typically going to be maybe one per year. The purpose of removing the major event days is to allow the indices to give a good indication of how does the utility normally operate. So as you design your distribution system, you've got normal operational stress and strain on it, and you want to know how do we normally operate, so you calculate the indices without the large events. Then you separately are going to analyze the large events. Usually the large events are going to be caused by disruptions to the transmission grid, whereas, as I mentioned earlier, most of the distributions are going to be caused by problems in the distribution system. But in doing so, just looking at the standard indices doesn't necessarily indicate what's really going on for a particular utility, because from the customer point of view, certainly you might understand why you lose power during a hurricane as opposed to a normal operational day, but regardless, your power is still out. Okay, the nice thing about these reliability indices is they allow comparisons. And here's a report with the reference given here that compares these two indices with the United States versus countries in Europe. And what you'll notice is that for the most part, our electric values, our outages at 240 are substantially higher than those in other countries, at least for the European countries here. Okay, this slide here gives a comparison of what the SAIDIs would be without and with the major events. And in the graph here, the major events are indicated in red. The calculation of the SAIDI with the major events is indicated in red. In yellow are the ones without the events. Right here, we note that when the major events are included, the value is 344. When the major events are excluded, it's 155. So while the major events themselves are quite rare, they're actually causing, in this analysis, most of the minutes of lost electric service. So here at the bottom graph here plots the SAIDI for the various minutes for the number of utilities that reported SAIDIs in that range. And you can see that without the major events, we're doing much better versus with the major events included. Some utilities are reporting losses of more than 700 minutes per year. Okay, now the next issue is how much does it cost to you to lose electric service? Okay, electricity certainly has a varying value, and hence the cost associated with blackouts can vary substantially. Okay, you might have a momentary blackout. Here, momentary is defined as less than 5 minutes, where if you're a residential customer, perhaps you weren't using much electricity anyways, you would have potentially very little cost associated with that. This is in contrast with perhaps you're an industrial customer and you're running a production line. For whatever reason, you don't have backup power available on that line. You have a very short-term outage. It shuts down production, and potentially that very short outage could cost you millions in interrupted production. When I'm talking to my students about this, I like to explain it in terms of the varying cost of electricity by using an analogy of them taking an exam. When they're taking an exam and they're using their calculator, they're using very little electricity. But the electricity that they are using to run their calculator has a lot of value to them for the time period that they're in the exam. So how much electricity is of value to you, and the cost can vary quite a bit. And certainly this is impacted by the duration of the blackout. As a blackout goes from minutes to hours to days, the impact can go up substantially. For example, if you've got a house and you're in the summer and your refrigerator goes out, very rapidly food could spoil. Or if you're in the winter and your heat goes out, you might very quickly get into a situation, if perhaps you're not home, where pipes could freeze and cause a substantial amount of damage. So the long duration blackouts impacting a wide area are what we might consider the worst case scenarios. Okay, now in talking about blackouts, it's useful to differentiate between the smaller distribution ones and what we'll call the larger scale blackouts. The North American Electric Reliability Corporation, which oversees the reliable operation of the electric grid in North America, go by the acronym NERC. NERC requires that utilities report events that have either more than 300 megawatts in lost electrical service or affect more than 50,000 customers. In looking at a 12-year period, actually no, that's a 22-year period, the folks here at University of Vermont actually looked at 861 events that were reported to NERC, but it should be noted that the utilities sometimes reported events that did not satisfy either of the criteria. So of this 861, they found that only about 300 actually met the criteria for a large-scale blackout. Okay, so the average blackout that met the criteria affected several hundred customers, but in going through the statistical analysis, there was quite a bit of variation. Okay, so the minimum was 50,000. Large-scale outages, such as the one that we had on August 14, 2003, affected more than 50 million people. So you have quite a bit of variation in the size of the blackout. Okay, and looking at the size of the blackouts over time, this graph here, taken from the same paper as before, plots the number of large blackouts per year from 1984 to 2006. As you can see from the graph, we are not decreasing the number of large blackouts as we go through this time period. In fact, the largest blackout in the time period, the one in 2003, occurred right here, affecting 50 million people, as I mentioned, and causing many megawatts of lost electricity. In fact, here the dark black color is for events that cause losses of electric service of between 30,000 and about 100,000 megawatts, whereas the white ones here cause losses less than 1,000 megawatts. So if we look at the year 2003, we had quite a few smaller events, where small is defined as between 400 and 1,000 megawatts of electric service lost, but the two large ones here certainly dominated in terms of the total power loss that year. Okay, looking at another table from that paper, the causes of large blackouts vary substantially. Certainly, if you look at it statistically, the largest of these is caused by equipment failure, where almost a third of the blackouts were due to equipment failure. But when you look at the number of customers that were affected, 57,000, these were not the large-scale blackouts that were affecting many millions. In contrast, if you look at a hurricane, tropical storm, much fewer of the events were caused by these, but they were affecting a substantially larger number of customers. So just looking at the causes in terms of the percentage, even of large events, is not always the most helpful. And what you might note on here is I don't see anywhere on here in which animals were causing large blackouts. So squirrels and other animals cause a large number of small blackouts, but they're not the cause of the large scale blackouts that affect hundreds of thousands to millions of customers. Okay, certainly a major cause of blackouts in the U.S. and around the world is weather. In fact, we might say the majority of the extremely large blackouts in the U.S. are due to weather-related causes. Certainly hurricanes have been in the news. We haven't had ice storms lately, but living in the Midwest, I certainly know that a large ice storm could knock out power for us for many days here. Tornadoes, we've seen tornadoes going across different parts of the country, causing a lot of devastation and certainly causing blackouts as well. Now I'm trying to figure out how do we reduce the risk of these types of blackouts from an operational point of view. What you can do the day of or a few days before these events are going to occur, there's really little that can be done operationally. Certainly you can do some operational changes that can help with quicker restoration. If you know a large weather event is coming, you can get crews in to help you with the restoration. But if a hurricane is going to hit your service territory, you're going to lose service pretty much no matter what you do operationally. Now that's not saying that some prior planning can't reduce the extent of the blackout. Okay, certainly during a lot of weather-related disturbances, the trees are going to fall on the power lines. So how many trees you have, whether they are tall enough that they can hit the line, that depends on what you're doing with tree trimming. So tree trimming can help you reduce the extent of the blackout. More longer term, you might also look at how much of your transmission distribution system do you have above ground versus how much of it is buried. Certainly lines that are transmission lines and distribution lines that are underground are going to be less affected by wind. Okay, but of course, undergrounding the electrical system can be quite costly, with some estimates ranging between 10 or 20 times the cost of building an overhead line. Okay, now this slide discusses the idea of what I've called the supersize blackouts. Okay, in 2010, actually it was 2009, they had a workshop, and then 2010 they had a report. NERC identified several high-impact, low-frequency events, HILFs, that could cause blackouts that they said would have a catastrophic impact. That is, the blackout could be large-scale, and it could be potentially quite long-term. And they broke this down into a number of different categories. They said the likely events were either a coordinated attack, which they said could be either physical or a cyber attack. They talked about a pandemic. They talked about geomagnetic disturbances, and they talked about electromagnetic pulses. A coordinated attack would be where a group decides to target your electrical infrastructure. And if it's physical, then they're physically destroying either high voltage transformers or transmission lines. Certainly that could have an impact on the system, but the people would have to be physically present. Another coordinated attack would be a cyber attack, where somehow people hack into the system, and by hacking in they're able to do control actions that take out the power grid. Both of these have the potential for wide-scale outages. The second one, the pandemic, is what they call a people event. A pandemic such as a flu bug that's quite deadly wouldn't directly affect the power grid, but it would be what they call a people event, where the people that are needed to operate the grid don't come into work, so you have a worker shortage, and that could cause a wide-scale blackout. The third one, the geomagnetic disturbance, is something that I've been doing a lot of work on along with some of my colleagues. Geomagnetic disturbances are caused by solar flares. The solar flare sends matter towards the Earth. This matter impacts the Earth's magnetic field, and that causes actually what we call quasi-DC electric currents to flow in the high voltage grid. These cause the transformers to saturate, and when you have a transformer being saturated, it tends to generate lots of harmonics. These harmonics can cause either rapid voltage collapse of the power grid or potentially heating in the transformers that could cause permanent damage to the transformers. A geomagnetic disturbance would have a continental impact. So if we had a large, actually it wouldn't even have to be if we had a large geomagnetic disturbance, it could potentially take out the power grid for all of North America. The issue that is currently being studied is whether that would cause permanent damage to the equipment or whether it would just be a catastrophic blackout, but something that we could recover relatively quickly from. The last of the supersized blackout potential causes that they identified was an electromagnetic pulse, an EMP. An EMP would be caused by a nuclear explosion in the atmosphere. How big the area is that's affected by the EMP would be dependent on how high up the nuclear blast occurs. This is obviously a human-caused event, but when an EMP occurs, it causes very fast electrical transients in electronics, which can destroy electronics, and then on a slightly longer time frame, it causes disturbances in the power grid that are actually very similar to the GMDs that can cause equipment damage. So as I mentioned, mitigation measures for all of these are currently under discussion. Okay, the type of blackouts that most power engineers, at least those of us who work in the transmission level, deal with are what we call avoidable transmission level blackouts. Okay, now many major blackouts cannot be prevented, such as one due to a hurricane or an ice storm. But there are quite a few blackouts that actually, if you look at them after the fact, they were quite preventable. And these are blackouts that have a time frame of minutes to hours that are not caused by a weather-related disturbance that's going to cause physical damage to the grid, or something like an earthquake that's going to cause physical damage, but rather they're just the grid is operated at a point where it shouldn't be operated. And several examples of these is there was a blackout in Tokyo in 1987 where the time frame from where something went wrong to the final blackout was 20 minutes. In the North American Western System, the WECC in 1996, they had about 6 minutes of warning that something was going on. In the Eastern Interconnect blackout in August 14, 2003, the duration of the event was over an hour. So if people had known what was going on, they certainly could have taken corrective action. Now, having said this, I should note that many blackouts that could be prevented actually are prevented, and hence they don't make the news. So there are probably more near misses than we would care to know. I had the opportunity in 1999 to be part of a DOE investigation that looked at several blackouts that had occurred that year. There was one on the Delmarva Peninsula in summer of 1999 in which they did lose service to some customers, but in looking at it after the fact, it looked like there was a near miss on a much larger voltage collapse that could have affected a much larger portion of the grid. and in deliberately shedding load, in that instance, the operators caused a localized blackout, but in the opinion of the committee, actually prevented a much larger scale blackout. Okay, one that I'll talk about in just briefly is the event from August 14, 2003. If you were impacted by that, it's probably something that you aren't going to forget relatively quickly. Here's a picture from a New York newspaper just showing the people coming out of New York when the power went out that day, which was in later afternoon on August 14th. More than 50 million people across the northeast part of the U.S. and Canada were affected. The image over here shows a satellite image of the lights in this region the day before the blackout and then the day of the blackout. And you can notice that most of New York City is missing there. Outages affected Toronto and a number of other cities. Okay, the causes of the August 14, 2003 blackout were detailed in the final report, and I would certainly urge everyone who's interested in blackouts to read the final report that was created by the task force. It's actually a very readable document, and it does a nice job of explaining what goes on to the non-specialist. Okay, the final report listed 4 causes of the blackout. The first was that FirstEnergy, which was kind of ground zero for the blackout, did not understand the inadequacies of their system, particularly with respect to voltage and stability. The idea here is that they were operating the grid in the way that, while it wasn't apparent at the time, after the investigation, it became apparent that this really wasn't the correct way to be operating the grid. The second cause was inadequate situational awareness by FirstEnergy. The idea is that they did not know, or certainly they didn't have enough awareness of what was happening to their grid. And the view of the committee was that if they had had that situational awareness, if they understood what was really going on, they might have been able to prevent the blackout. The third was that FirstEnergy failed to adequately manage their tree growth. The blackout on August 14th was initiated by the loss of 345 kV transmission lines. After the fact analysis indicated that each one of those lines was tripped due to contact with a tree. In fact, I believe that on one of the lines that went out, there was actually a tree trimming crew that was quite close to the location where the line tripped. So that very day they were trimming the trees. Unfortunately, they didn't get to the one that caused the line to trip before it tripped. Okay, and then the last cause was that the reliability organization, primarily MISO, did not provide effective diagnostic support. So the conclusion from the committee was that with these 4 causes, for the most part, better cyber-human interaction would have helped, along with better tree trimming. So what could have occurred in this blackout? Well, with hindsight, the blackout certainly could have been prevented. And I think that was a conclusion reached by the committee. A smarter electric grid might have provided the necessary situational awareness, so they would have known that they were getting into a precarious situation, and would have been able to do the dynamic load reduction that would have been needed to keep the system from cascading into the large-scale failure that affected 50 million. So it might have been a localized outage, but certainly it should not have been an outage that affected a good portion of the Northeast. Okay, but in doing this, the key issues that need to be addressed is which grid improvement costs are justified and what are we missing? What will be the next large-scale blackout? So since this occurred in 2003, lots of work has been done on the U.S. power grid, and hopefully our reliability is improving. But in doing these, you do have to look and say what is justified and what is not justified. For example, burying a transmission line can reduce the outages on the line, certainly due to weather-related causes, but that will be quite costly as well. Okay, having said this, I should note that the effects of short-term blackouts can be eliminated or reduced through the use of UPSs and backup generation. Okay, if you've got some electrical load that really needs higher reliability, it makes sense to put it on a UPS, and it makes sense to protect it with backup generation. As I noted, I live in a location where I get relatively frequent power outages. So since I work quite a bit on my computer, I've got my computer on a UPS. So when the lights go out, my computer stays on. I also have a backup generator. So when the lights go out, they'll be out for perhaps 30, 40 seconds. My backup generator will sense that the power is gone. It'll start up. And within about a minute or so, most of the house is back running. Now, in doing that, of course, it's important to have sufficient fuel supply to run the generation. Okay, a new trend that is being developed is what's called microgrids. A microgrid is setting up an interconnected electric power grid which has the ability to run autonomously from the main grid and offer the potential for additional reliability. So a microgrid is one where you take a number of smaller generators, set them up in such a way that they can run interconnected, and then have the necessary control systems in place so that if you lose the main electric grid, you can operate autonomously. Microgrids are an area of active interest by the military right now, where they'd like to have the ability to run a military base that is normally supplied by the regular electric grid autonomous. So if the grid goes down, the military base can stay operating for, I believe, up to 6 months at a time. So in doing this, you have to have sufficient generation capacity available locally, and you also have to have a long-term fuel supply in order to operate autonomously. Lots of locations have backup generators, but what's important in looking at those backup generators is to see how much fuel, such as diesel or natural gas, do they have available, and how long they could actually supply the load for before they run out of fuel. Okay, the last topic associated with blackouts is restoration. The cost of blackouts certainly increases the longer the power is out, as I already mentioned. So how quickly power can be restored depends upon what caused the blackout. If you've got a lot of equipment damage, such as down power lines from an ice storm or a hurricane, it's going to take much longer to restore power than if you just had a failure, let's say, caused by a squirrel, where you get the squirrel out, the protection system operated correctly, you can then very quickly restore electric power. When you have a flooding situation, as we saw recently in the New York City area, and you've got houses damaged by flooding, if you get water into your electric wiring, before you can restore power to the neighborhood, you need to make sure that all the houses that have damaged wiring are disconnected. So there's an added time associated with going around and disconnecting houses, where the electrical grid, if you were to try to reconnect it, you'd just get an immediate short circuit. Also, when you have a large-scale outage, some generations, such as nuclear power plants, can take days to restart. I know after the August 14th, 2003 event that the nuclear power plants, some of them were down for many days as they tried to get them restarted. A last issue, and this is something that we've been looking at with the geomagnetic disturbance problem, the GMDs, is if you have damage to your high voltage transformers, that could be really catastrophic if we lost more than a handful of these transformers, since the transformers are relatively unique in their design and we don't have a lot of spares available. Last, I wanted to show a graph here that came from the University of Vermont report by Paul Hines. This shows the dots here are on a log-log scale between the blackout duration in hours and the blackout size in megawatts. What they noted, and this is using the NERC data, is for larger blackouts, there appears to be little correlation between the size of the event and the restoration time it takes to get power back on. So if you look at this, pretty much regardless of the size, you don't get a correlation there. You can have events that are very large and power is restored quickly, and you can have events that are relatively small and power takes a long time to be restored. So what's the conclusion? We certainly know that we're more dependent than ever on reliable electricity. And people ask, can we eliminate all blackouts? And the answer is no. In the bulk power grid, we really can't eliminate all blackouts. If you have a power grid that is subject to tornadoes, hurricanes, earthquakes, you're going to have times where the electric grid just goes down. But certainly there are categories of blackouts where we can prevent them from occurring, and that's what we're working hard to do. So we certainly can reduce their incidence. In doing this, though, as I noted, there's a cost-benefit trade-off. If you have electric power that you really need to have on with as high reliability as possible, as I mentioned, UPS, backup generators, and microgrids can help provide that high reliability. Thank you.